In this part, we will learn about variables and design grids. So before we learned on factorial design and how it's so powerful and why it beats trial and error. We also learned the fundamental difference between independent variables and the difference from dependent variables. Now, in the following part, it will be more practical. So we will learn how to set up a factorial experiment. We'll define our variables precisely, choose the levels, and build a design table that tells us exactly which experiments to run. So hopefully by the end of this part you will have a complete experimental plan that you are ready to execute. So this model shows the structure of our factorial experiment. Two inputs, x1 and x2, go through our tablet manufacturing process and produce an output y. The design systematically varies both inputs to understand their combined effect on the output. Our independent variables are the cause in our cause and effect study. So these are the inputs that we control. Also, we said they are called factors. So they're like recipe variables or process parameters. In our tablet example, x1 is binder amount in percentage, as we mentioned. So often is used as described as weight by weight. And x2 is the compression force in kilonewton. Critically, these must be truly independent. So changing x1 should not force x2 to change. The dependent variable is the effect we measure, our output, as we mentioned before. Is the response, is the quality property, or the outcome. In tablet formulation, this could be the hardness, as we mentioned in our example, in newtons. Friability can be expressed as a percentage, or disintegration time is in minutes. Remember, we will need one equation for each response we measure. So if we want to optimize multiple properties, we will build multiple models. So now let's talk about something that might seem strange at first time, which is basically this kind of coding. So instead of using the actual values like 2%, 4%, 6% for the binder, we're going to use a coded value. So here, as you can see, -1, 0, +1. And these represent low, medium, and high. So why do we bother with this kind of coding? There are several reasons to do this. First thing, it allows us to standardize everything. So binder might be measured in percent, while force is measured in kilonewton. So coding, using this kind of code or standard normalization, if you like to call it this way, it will put them both on the same scale. So they'll all be scaled from -1 to +1. And the second reason, it makes the mathematics behind this easier or simpler to understand. So the regression equation is easier to calculate and interpret when we have this kind of system. And finally, it will allow fair comparison. So for example, if the coefficient for x1 is 12 and for x2 is 19, we can immediately see that x2 has a bigger effect. The center point, which is normally given a 0 value, is always the midpoint of the range. Here you can see how the three levels map onto our experimental factors. So each factor has a low, medium, and high levels, and as you can see, they are evenly spaced using its axis. This creates a systematic grid of test points. Choosing levels is a critical decision you must make before experimentation. Base your choices on literature, pilot studies, and equipment limits and safety considerations. In many cases, we refer to pharmacopoeial standards, such as the British Pharmacopoeia, or some reputable sources, such as the Handbook of Pharmaceutical Excipient, to find a good range for our variable. The low level should be the minimum feasible or meaningful value. The high level should be the maximum feasible or meaningful value. And the main thing here is to remember the medium value or level must be exactly halfway between low and high. So this is quite important, is to make sure the spacing to be equal. So the distance from high to medium must be equal to the distance from medium to low. For our tablet experiment, here are the 4 chosen levels. So as you can see, for x1, which is the binder concentration, when it's low at -1, that is 2%. That means 2% of medium of the binder concentration, and we assign this as the low value of the range. The medium range, which is 4%, we assign it 0. And the high is +1, which is 6%. For x2, which is the compression force, low, which is -1, is 5 kilonewton. The medium at 0 is 10 kilonewton, and the high at +1 is 15 kilonewton. So you can clearly see here the equal spacing, 2% increment for binder and 5 kilonewton increments for force. So here is our complete design. As you can see in the table, it shows all the 9 experiments. Each row represents one formulation to make and test. The table shows both coded values, which we said we assign a number from -1 to 0 to 1 for analysis, and actual values for manufacturing. This is basically what you could consider the experimental blueprint. So if you look at the experimental space, we see 2-dimensional grid. The horizontal axis shows the binder concentration from low to high. The vertical shows the compression force. So this is the testing area. As we place our 9 experiments on the grid, we can see how they systematically fill in the testing area. Every corner is covered, the edges are covered, and the center is covered. This ensures we will detect any trends that are possible, or so that we find the optimum value.